So let's look at this statement. Okay. Super straightforward word problem here. 10 is 3 more than a number. So if I look at a number line, I've got 10 sitting here. And I know that's 3 more than some number. Let's call it n for number. So if I translate that, 10 is 3 more than some number n. And just, I'm assuming that both of these are positive. It's not, of course, always going to be the case. So here's our number line here. Now, I've got these two fixed points. I don't know the value of n. I know 10 is more than that. I know this distance is 3, so we can figure that out. But let's think about what's going on here. If I have 10 and I subtract 3 from that, and I have n and I subtract 3 from that, notice the 10 is still 3 above the n. Whatever I'm doing to this, the relationship of being more than is still the same. This distance between them is still going to be 3. So if n plus 3 is equal to 10, if this is actually the same as this, if I'm subtracting 3 from 10, that's this, and I also subtract 3 from n plus 3, I'm going to wind up at the same spot, right? N plus 3 minus 3 is n, and 10 minus 3 is 7. So if 10 is equal to n plus 3, then 7 will be equal to n, and now I know the value of n that makes this true, right? 10 is 3 more than what number? 10 is 3 more than 7. 7 is the only number that's 3 less than 10, right? There's no other value that would match exactly this spot if I went 3 below this starting point. So I would say the solution is, or the number is 7. There's just a single number there, right? And I could put a dot on the number line to show n is 7. Well, if I start over and I leave out one word, oops, it's a slightly different situation, right? In fact, more than slightly, it's a very different situation. If I put my number line up here, I can put 10 on my number line. I have no way to know exactly where n is going to be. 10 is more than a number. Is 10 more than 9? Yes, that's true. So the number could be 9. Is 10 more than 7? Yes, 10 is more than 7, so n could be 7. Is 10 more than 0? Yes, it is. So 10 is more than 0. That works. Let's try negative 10, not to scale. Is 10 more than negative 10? Of course, it's to the right of negative 10. Every number over here, 10 is more than that number. Right? Every number over here is less than 10, which means 10 is more than that number. I could go away from my integers, say 9.5. 10 is more than 9.5. I could look at pi, and about 3.14159265358, and so on. Right? 10 is a lot more than that. It's more than 4, it's more than 3, it's more than pi. 10 is more than every number over here. And so there are two things we notice when we're solving inequalities. When I start with the statement, not 10 is equal to some other expression, but when I say 10 is more than, this phrase together without a number in between is an inequality. I'm not saying 10 is exactly this distance away from something else, or 10 is exactly double something else. All I know is that it's to the right of something else. So any number over here works. So all I can say is any number that's less than 10 satisfies this statement. So there are a few ways we can represent that. Often we're just kind of lazy and we say this. Just like up here, we're often lazy and we say n equals 7. Right? We kind of all know what that means, so we just say that. But technically when we say the solution is 7, 7 itself is our solution. That value is the value of the variable that's making the statement true. Here I don't just have a single value for my variable that will make this statement true. I have an infinite number of values that make that true. So we have to be a little more careful. So we can get into set notation, and I can say the solution set is all numbers, column X, just because we need some index to refer to them, such that this condition is true of each of these. What's true about this? It has to be a number less than 10. Any number that fits this condition is going to be one of the elements of our set, and we say that's a set by putting braces around it. Now, that's somewhat advanced. We haven't really gotten into set theory, but this is one way to represent the set. When we're looking at a number line, though, we have a different way to show that. But before we move on to that notation, I want us just to look at this number line for a little bit. When we're looking at our solution to an equation, it's just one number. I can show that on the number line really easily. Boom. Just look at 7, just that one point. That's it. When I'm looking at this set, I'm looking at all the numbers, including 7 and 7.1 and 7.004 and 9 and all of these other numbers. So I'm shading it in forever. So some people like to squiggle, some people like to do a curvy thing. What you don't want to do is just shade it in like this. It's not at all obvious that this is different from this. Right? That this side has been shaded in more heavily than this side. So even if you go back and forth, now it's a little better, it's still kind of subtle. I think giving some width to your shading in is ideal. You don't have multiple colors, you don't have a highlighter function when you're writing this in your notes, right? Maybe you do, maybe you have a pack of highlighters with you that works. Some thick markers, but shading it in if you're just using pencil, that's a good way to do it. Now what we have to indicate is where does all this shading end? Right? If I'm putting this on a regular number line, I don't just have a little mark at 10. Right? We usually also have marks at 11 and 12 and 13 and 9 and 8 and 7 and 6. So it's not really clear here exactly where this shading ends. And so that's where we need to indicate it to say this spot 10 is my spot. Just like I put a dot at 7, I'm putting a dot at 10. So let's look at the various situations here. we'll just stick with 10 because we need some number to compare it to. So let's change our color again here. If I'm saying my variable, whether it's n or x, whatever it is equal to my number, I'm going to put a dot at that number. If I'm saying it's not equal to the number, I'm trying to shade in all of this and all of this, but not 10. Right? You can be any number you want, but you can't be 10. So instead of a dot, I'm going to put an anti-dot. I'm going to put an open circle right at 10. And that's how I can show everything's shaded in except for 10. Well, if I have less than 10, is 10 less than 10? No, it's not. So I'm not shading in 10, but I am shading in everything else. Or I can say x is less than or equal to 10. I actually have two conditions here. Is 10 less than 10? No, it's not. But is 10 equal to 10? Yes, it is. Is 9.3 less than 10? Yes, it is. Is 9.3 equal to 10? No, it's not. But that's why we don't say less than and equal to. You can't be both less than and equal to some other value, but we can be less than or equal to. And so in our regular algebraic notation, we indicate that with a less than symbol and half of an equal sign underneath it to show that all of this counts. Now this doesn't stop where my number line stops. Or if I put a scale on here, 9, 8, 7, 6, 5, 4, I'm not stopping at 4. I am going on forever. This one goes on to positive infinity as well. Right? So those are our options there. All right. Now one more situation. Try to fit this all on here so we can compare it. In lots of real-world situations, we're not just saying Eric is less than has less money than Jimmy, or Eric has fewer cars than Jimmy, right? Eric is younger than Jimmy. We're comparing the value of x to two different constraints. We're saying x is between 10 and some other value. Let's say 3. So the place where I see this probably most often is in age-based pricing, right? You're allowed into the museum for free if you're 3 or younger. If you're older than 10, you're considered an adult, and so you have to pay full price. But for the child fare, I don't know what the extra on there, the child fare, the child price to be admitted, you're between the ages of 3 and 10. So if you're 10 years old, that counts. So less than or equal to 10. If you're exactly 3 years old, you can pay the child price. But if you're more than 3, then you have to pay. If you're exactly 3, then you can get in for free. You're younger. But if you're more than 3, you have to pay the child fare. So I can look at 10, and I can look at 3. And I can say, okay, if I'm 4, does that count? Yes, 4 is in between. 5, yes. 5.5, yes. 9.9 years old, yes. 10 years old exactly, yes. All of this counts, including 10, right? I'm including 10. I'm excluding 3. I'm saying x can't be exactly 3. And so my graph is bounded on both sides. One way to write that as a solution set is to say all x such that x fulfills this criteria. X is greater than 3, and it's also less than 10. It's in between 3 and 10. 15 is greater than 3, but it's not less than 10. It's not sandwiched in between here. 2 is less than 10, but it's not also greater than 3. So this is an AND statement. X is greater than 3, and it's less than 10. It's in between 3 and 10. Now, a simpler way to write this is just to list the endpoints. So if I switch colors here, I can say 3 is my left boundary, and 10 is my right boundary. 10 is the largest number x can be here. There's no limit to how low x can go. 10 is my upper limit here. Oops. 10 is my upper limit here. There's no limit to how low I can go. 10 is kind of my upper limit, but I can always go lower. And now we're getting into some higher level set notation. This set on the left is being joined with this set on the right, where 10 is now my lower limit, and I can't get, I can go as high as I want. There's no limit to the right, so that's positive infinity, right? Hopefully you know this sideways 8 is infinity. That's what this symbol represents. Now, I'm getting into this more complicated set notation because there's another way to draw these graphs. Come on, I just want to move you over. Okay. Now, the dot notation here is kind of nice. It goes along with this is equal to, right? I'm indicating this point. That's great. One challenge with the dot notation is these big, like, barbell ends are not very precise. If 10's the only number I'm putting on here, obviously 10's the number I care about. But if I'm trying to show 9.8, and my number line already has all the integers put on there, it's not really very precise. However, we have these symbols here that are just a straight line. So another way to show all of these inequality solution sets, is, let me, this is super precise here, is to show 10 is included, 3 is excluded, and I'm looking at everything in between. Oh, that went a little too far. Stop right there. Okay. Up here, x is less than or equal to 10, so I'm looking at 10, looking at all the things that are less than 10, or it could be exactly 10. Here I'm looking at all the numbers that are less than 10. Right, both of these go on to the left forever. But then when I get to 10, I'm going to put a parenthesis there, right at 10. And I'm trying to be precise to go right at 10. So what's the difference between a bracket and a parenthesis? In this context, the bracket, let's shift colors here, indicates that that endpoint is included. I'm not putting a bracket here because it's on the right. I'm putting a bracket with the 10 here because I'm including 10. 10 is part of my solution. 10 is less than or equal to 10. 10 is less than or equal to 10. Here, 10 is not less than 10, so 10 is excluded. Because I don't have an equal sign here, I use the parenthesis for that endpoint. Here 10 is not part of the left half or part of the right half. So if I go back to my right here, I'm looking at 10. I'm less than 10. That's this part, or I'm more than 10. That's this part. So it looks almost like an X kind of thing here, parenthesis going each direction with both of them being at 10. Now it kind of breaks down when we're just looking at the point 10. I don't know if I'm curving to the left or to the right, bracket to the left or bracket to the right. I'm not doing either because I'm not including these numbers or these numbers. So when it's just equal to, we're just going to put a dot there. We don't really have another choice. So some textbooks use this bracket or parenthesis notation for graphing. Some books use the circles, the dots, for graphing. What we need to pay attention to is this endpoint part of my solution set? If I'm strictly less than or greater than, I'm going to not include that as part of my solution. So it's an open circle, it's the parenthesis. And if I was saying x is greater than 10, I would do the parenthesis going this way. Right? If I am including it, that's a filled in circle, right? It is part of my solution. It's a filled in circle. It's a bracket. So if I'm doing greater than 10, the bracket's going to face x is greater than 10. It's going to face the way that I'm shading in here, right? So here I'm less than 10. It's brackets pointing to the left. I'm greater than 3, parenthesis pointing to the right. Parenthesis because 3 is excluded. Open circle because 3 is excluded. Filled in circle because 10 is included. Bracket because 10 is included. So that's how we're graphing our solution sets, because for inequalities, our solution is not just a single number. It's an infinite number of numbers that all fulfill that particular criteria.